Marcos, thank you for also being here. So Marcos is a professor at the Universidad Estatal de Campinas, graduated from language teaching in 1999, if I'm not mistaken. So thank you very much.
Thanks, Fernando, and thanks for the opportunity to give this talk too. So this is a celebration of 50 years of Nigel's mathematics. Yeah, so I decided to talk about this date. So almost 46 years to the date. And this is in my opinion, this is a very influential paper. It really changed a lot of things, and for me especially. So let me try to convince you of that. So it's 1,300 plus citations. And I found a couple of days ago 276 papers with ADHM in the title. And this covers only like the last 25 years, perhaps. So a few highlights among these are 276 papers. So first, it's a Whitman's paper on the which is translating the ADHM construction done in the paper I've shown you to some physics. I don't know what that is. And then there is Nekrasov and Schwartz paper a few years later, adapting the ADHM construction to do the non-commutative bounds on R4, which is very nice. This is very nice paper. Nakajima's construction of the adaptation of the ADHM construction to construct holomorphic or better said torsion-free sheaves on CP2. So he describes the moduli space of framed torsion-free sheaves on CP2 by an adaptation of the ADHM construction. That includes, by the way, the Hilbert scheme of points on C2, also included in this construction. And it has, a whole story behind that as well. We could diverge it and talk about a lot of the stuff that Nakajima did. Many of the adaptations that Nakajima and other people done following this paper. So one of my first contributions to this is this paper in 2008 with Igor Frankl, where we did a construction like adapting Nakajima's and looking back at the original construction. We looked at all the torsion-free sheaves on CP3. Now this is should be a framed Instanton torsion-free sheet on CP3. And also another paper of mine with Shevepitsky, in which he used the ADHM construction to show that the moduli space of Instanton bundle on CP3 is smooth. That was an open problem for a while. And part of the legacy of the ADHM construction is also the NUM transform. And then there's a whole history and many papers written about the NUM transform, which is also an adaptation of the ADHM construction to translation invariant Instanton and R4. So this is the legacy of this paper. Let me tell you a little bit about this ADHM construction of Instanton. It starts with this what I like to call the twistor diagram. It also goes back to the beginning of Nigel's career, I suppose. So on the on your right-hand side, there is a CP3 and the twistor map down to S4, in which the fibers of this twistor maps are lines. So there is this extra point, this point at infinity of R4, and over there is the corresponding line at infinity. So S4 is this one-point compactification of R4. Choosing a complex structure on R4, you get C2, right? So choice of a complex structure on C2. And if you add the line at infinity, you end up with another compactification of R4, which is this CP2. And the CP2 is one particular choice of CP2 that contains the same line at infinity that on the right-hand side of the diagram. This is the twistor diagram. And the twistor lines are supposed to parameterize, well, they are not supposed to, they do parameterize all possible choices of complex structures on R4. Right? So if you choose one particular choice of complex structure, it's like you cut, you also have a projection, right? So from a CP2 to S4, which is the composition of the horizontal map. Well, I have this pointer here. Except that I don't see it. Okay, here is very faint. So the composition of this horizontal arrow with this vertical one gives you a map from CP2 to S4, which is like a blow-up. It's one-to-one away from the point of infinity, and at the point of infinity, you have a whole line. So that's this is the choice of complex structure on R4, right? So cutting all the other twister lines on CP3, except that it contains this special twister line over the point of infinity. And this diagram can be adapted to higher dimensions. S4 is HP1, so you can change for the other quaternionic projective spaces here, for which the twistor space is these odd dimensional complex projective spaces. You can also substitute S4 for other quaternionic Kähler manifolds, like the Grassmannians of planes in C K plus 2. The simplest example is CP2, right? So if you put K equals 1 here, you get P2, and the twister space is the flag manifold. And this is also one of Nigel's first papers, right? So that the only two Kähler twistor spaces were the flag and C3. There's this other interesting example, which is the third symmetric Wolf space in 8 dimensions, which is a G2 mod this SO4. The twistor space is G2 mod some parabolic group. Also interesting story going on there. But today I'll focus just on CP3, at least in the beginning. In the ADHM construction goals, it's a big diagram, really big. Go back here a while to see it. So let's see. So the starting point are the instantons on S4. The starting point is on the bottom here is the instantons on S4, framed at infinity. So the goal of Atiyah, Dream, Vision, and Money was to make a complete construction of these instantons on R4. Before there was a paper constructing some, or a bunch of paper by physicists constructing some particular families. And their approach is to use something that was previously known, the Ward correspondence, or Atiyah Ward correspondence, which relates these instantons on S4, framed at the line of infinity, with a class of holomorphic bundles on CP3, the twistor space of S4. Right? So from the instantons, you go to some holomorphic bundles on CP3. And they took advantage of some new constructions of in algebraic geometry, relating that to what we now call the ADHM equations. It's one of the things I like about this paper is the economy of the abstract. Right? The abstract is complete construction involving only linear algebra. So that's the linear algebra. So ADHM, this in red in the middle is the linear algebra. So the ADHM equations are some equations involving matrices. You have 4 matrices. I'm not going to really write the equations today, but it's just in the end, it's a bunch of quadratic equations on the coefficients of these matrices. And they figured out how to construct all these holomorphic bundles on CP3 out of these matrix equations, out of linear algebra only. And also do this arrow here. So this was more or less understood at the same time. A few years later, Donaldson, a young Simon Donaldson, made this correspondence between the ADHM equations and holomorphic bundles on CP2. The difference here is that the holomorphic bundles on CP3, we need some extra structure, some reality conditions, some real structure. Plus some vanishing. This Instanton word here is some vanishing on the cohomology coming from the field equation. Now on CP2, you get all holomorphic bundles framed on L infinity, right? On this line at infinity, right? Without these additional constraint here of the reality and the Instanton condition. Right? So Donaldson made this line here. This correspondence here is another student of Donaldson, a guy named Wu, also in the 80s. This arrow here is just restriction. You get the bundle on CP2, and then you restrict to a special hyperplane containing at the line's infinity. So this is just restricting the holomorphic bundle. And I never seen this direction from CP2 to CP3 done without going through the ADHM equation. Right, so if you want more, there is a recent expository paper by Simon Donaldson on the arc. But the main topic of this talk is these objects, Instanton sheaves. Right, so the Instanton sheaves, they start with the ADHM paper in '78, and it's taken by algebraic geometers in the 80s, and starts on a path on a life of its own. Right, so this is the definition. The definition is maybe too technical, not so important, but the important thing here is that there are a bunch of cohomological conditions. Just some torsion-free sheaf on a complex projective space. Now it doesn't have to be. If you're doing algebraic geometry, right? You don't need to worry about complex numbers anymore. You can work with whatever field. But it's some torsion-free sheaf on PN satisfying a bunch of holomorphic or a bunch of cohomological conditions. Some of these cohomological conditions are reminiscent of the physics, right? So they come about because it reflects the fact that some field equations have no solution. What is it? I forget the right physics words, but it's something like the Laplacian has on a positive curvature. The Laplacian has no solutions, so that's reflected on this cohomological condition. Right? So these are the definition of an Instanton sheaf, which generalizes the holomorphic bundle that appeared in the original paper by ADHM. And it turns out that all these cohomological vanishings are equivalent to this fact that the Instanton sheaf is the cohomology of a monad. A monad is a complex, three-step complex like that, for which the first map is injective, the second map is a surjective, and this complex only has the cohomology in the middle. And that's what we call the cohomology of the monad. So this is a complex, right? So beta composed with alpha is 0. And the mathematical Instanton bundles that were introduced by O'Connor and Spindler, based on a paper by Salomon a few years earlier, it's the mathematical Instanton bundles introduced in '86. They are examples, right? So they are very particular cases of these Instanton sheaves. So these Instanton sheaves are now not just for odd dimensional projective spaces, but they are for any projective space, and you doesn't need to have a particular rank, can be of arbitrary rank, and also they don't have to be locally free. So this is generally of this. It turns out that it's also interesting, important to consider some degenerations in some sense of the Instanton sheaves, which is this thing that we call the perverse Instanton, and also the rank 0 Instanton. Now, oops, wrong button. So before we were talking about monads, now we take objects in the derived category, so things that are quasi-isomorphic to complexes like that looks like a monad. Maybe I should say what is this VC? VC is any vector space of dimension C, right? And same thing for V R plus 2C, and vector space over the field that you are considering of dimension R plus 2C. So the first map here, alpha, is supposed to be injective. That's what it means that H minus 1 is 0. First map is injective. But the second map here doesn't have to be surjective anymore. You may have some extra cohomology here, H1, but this is codimension 2. So it's a torsion sheet supported on a sub-variety of codimension 2. This H1 sheet. And H0 is a torsion free sheet that are appearing here as the kernel of beta pushed out by the image of alpha. But it doesn't need to be an Instanton sheet anymore, in the sense of the definition. And the rank 0 Instanton is just a perverse Instanton, what I said before, but with no cohomology in the middle. So it's some codimension 2 sheet that has this complex as a resolution. And one example is this, right? So if you take the derived tool of a non-locally free Instanton sheet, what you get is one of these guys, right? It's the middle cohomology of the dualized complex will be some torsion free sheet, and the H1 of this dualized complex will be a rank 0. So you can think of these perverse instantons as appearing as duals of the non-locally free instanton. For the instantons, the dual of a locally free instanton is always an instanton as well. But then this duality can break apart if you take stuff that is non-locally free. And this is a way to fix that. Good, but then, we mathematicians, when we don't know how to solve a problem, we generalize, so that's what people did. But for good reason that I'm going to try to convince you. So Sasha Kuznetsov and Daniele Faenzi, more or less at the same time, these are the dates of the published papers, but more or less at the same time, they thought about this a way to generalize. The P3 is the easiest example of a funnel threefold with PK rank 1. And so, why don't we try to use this machinery that already had 30 plus years of instantons and try to bring this nice special class of bundles to some other type of funnel threefolds. So they came up with the following generalization. Right? So my funnel threefolds today, for the purpose of this talk, will also be a funnel threefold with the current one, even when I don't say that explicitly. And then you can consider the index of this, which is IX. IX, the index of a funnel threefold, can be 4, 3, 2, and 1. And you can rewrite, these numbers in that way. Right? It's 2k plus Rx, with this remainder being either 0 or 1. So, for instance, in the case of P3, the index is 4. QX is 2, and the RX is 0. So an instanton bundle will, in their definition, is a mu-stable rank 2 locally free sheet, whose degree is proportional to this remainder, and you have one particular vanishing, which is the same vanishing as for P3, because QX is minus 2. So one particular vanishing that appears on the P3 case. Right, so they had this idea of matching the so-called instanton condition, which is this vanishing of H1 here, that appears on P3, precisely because H1 via these 10 rows correspondences can be tied with the solutions of the coupled Laplace equation. Right? So since Laplace equation has no solutions, that's why the corresponding holomorphic bundle of CP3 must have this vanishing. Right? So there's no twistor space, you know, all the relation with physics is gone by the time of this definition, right? But that's what that's how they adapted it, right? So this vanishing of H1 here is now the so-called Instanton condition. So it's really a generalization of P3. And they have some very nice results about this. So in particular, in Daniele's, Faenzi's paper, he also has a monadic description for a bunch of these instantons in several examples. So a lot of what was done for P3, or some of what was done for P3, can really be adapted to this more general practice. And even more recently, there was some further generalization of this notion of instanton bundles for arbitrary projective variables. But I'm not going to dwell too much on it. Good. Now, just well, last year with a postdoc of mine, a guy at Comaschi, we, you know, by now, you know, this is the non-locally free guy. So that's me, right? So the guy that takes the locally free, the bundles and see what happens when things degenerate. So we introduced this notion of an instanton sheaf for the other, for these Picard rank 1 threefolds, product threefolds. Now just the vanishing of H1 is not enough. You need also a vanishing of H2, which is, this is the vanishing of H2 that you get for free when the sheaf is locally free. When E is a bundle, you get this for free just by set duality. But when it's not locally free, you really have to impose this. And you really have this, perhaps this weird condition here that the for the final threefolds of odd index, you can only have these instanton bundles with even rank. And these guys also have monadic description and so on. And one theorem that we proved that I think is interesting is that when you are talking about the no locally free instanton of rank 2, the sheaf double dual is always locally free, right? So it doesn't have to be, right? So the sheaf dual is always reflexive. It doesn't have to be locally free. But for these instanton sheaves, they are locally free, and they are also instanton. So they also satisfy these cohomological vanishings.
Sorry, can you remind us what is the semi-stability?
Semi-stability, yeah, sure. I should have written here. It means that any subsheaf, the slope, so for each bundle, we can define what is the slope, degree divided by rank. Right? So for every subsheaf, that's model. Yeah, thanks. Sorry about that. And then the quotient of the double dual by the sheaf itself is a rank 0 reason. So in some sense, that you can reconstruct every non-locally free instanton out of the locally free ones, just by making some modification along this quotient. So maybe I can write it. Not with red. Maybe with black. So you have a sequence like that. E is a sub of its double dual, and this is the quotient that I'm calling QE. So if you start with something that is an instanton, this is going to be a locally free instanton, and this is a rank 0. Now, if you start with a locally free instanton and some epimorphism on some rank 0 instanton, the kernel will also be a torsion free. So the torsion free instantons are always obtained and constructed in this way. That is the moral of this. So this is for all threefolds with char rank 1. And one way to rephrase this instanton condition is in a more categorical or derived categorical way, is to say that the instanton sheaf will always be perpendicular to this particular sheaf which is always present as a generator of the derived category of the Comaschi people. Right? So these guys,
What is this word?
something of correlation to, pure correlation to. Yeah, whatever curve. Yeah, not necessarily smooth, can be non-reduced. This is the point that I start talking about Bridgeland stability, right? Because when I started learning about Bridgeland stability, people were trying to construct examples of Bridgeland stability in this or that example. And I said to myself, okay, but I want to see as a Bridgeland stable object, what a Bridgeland stable object looks like. In the literature, they were doing ideal sheaves and something like that. No, I want to see one. If my favorite bundles are Bridgeland stable in some sense, right? My favorite bundles or my favorite sheaves are the Instanton. So that's what I'm trying to lead here with the next frontier, right from the path. So maybe I won't spend too much time talking about Bridgeland stability. So Bridgeland stability is a notion of stability now, not only abelian category, right, like the abelian category for coherent sheaves, but on some triangulated category, right? So Bridgeland stability takes two actors, so the heart of a T structure. So some abelian subcategory of your triangulated category T, and some homomorphism called central charge from the Grothendieck group of the abelian category, which of course matches the Grothendieck group of T to the complex group. So this is the central charge. And the central charge has to satisfy a few technical conditions. It factors through some lattice, which is this capital lambda here, and some finite dimensional lattice equipped with a norm, and and then satisfy some axioms, right? So never mind too much what the axioms are, right? It's much of technical things. The most important of them, perhaps, is this one about the every object always admits a Hardy-Narazino filtration. So in some sense, it is supposed to look like sheaves, look like a category of sheaves. Good. So maybe I'll give you one very simple example, which is sheaves on curves. So if X is a smooth projective curve, then triangulated category will be the derived category of coherent sheaves on that curve. And the usual slope, right, degree and rank, you can arrange as being the real and imaginary part of your central charge. So everything fits the various conditions there, the various technical conditions, and the important thing about this slide is this last phrase in blue there, that slope stability for sheaves on curves is a Bridgeland stability. Slope stability is Bridgeland stability. Right? So Bridgeland stability is supposed to generalize this to higher dimensions. Wait, but we do already have generalizations of slope stability for higher dimensions, right? It's called Gieseker stability. And we're going to see how they match. Maybe this is not so important either. This whole slide is just telling you how do people first constructed examples of Bridgeland stability conditions on surfaces. So just the usual, just taking the category of coherent sheaves on surfaces is not enough, right? It's not going to lead you in any way to a Bridgeland stability. You have to do this a procedure called the tilting on a torsion pair, right? So you end up with a bunch of subcategories of the category of coherent sheaves parameterized by some parameter, parameterized by some real number beta, and you perform some derived category magic, and you make called tilting. You obtain a new heart of a T structure and some cleverly devised choice of the churn classes gives you what is this central charge. So now the central charge involves not only the degree, which would be C1, right, the first churn class here, but also involves the second churn class, the second churn character. Right? So this is something that involves all the churn classes of an object on a surface. For trifolds, the story is a bit more complicated because the previous procedure is not enough. You have to tilt again. You have to perform the trick a second time in order to get Bridgeland stability condition. And when you perform this trick, you add a parameter. And so now our torsion pair is depends on two parameters. Beta is real, any real number. Alpha is supposed to be positive. Then, you know, bunch of technical stuff. You end up with a family of categories, this A, alpha, beta, which are the first element in the Bridgeland stability condition. This is the heart of a T structure. So now the abelian category that is replacing coherent sheaves. The abelian category depends on two parameters, alpha and beta. And you know, you or they, right? So Bayer, Macri, and Toda, they figured out what is the central charge in this case. Now something that involves the third churn class as well. It involves all the churn classes again, and you get a bunch of a family of Bridgeland stability conditions that now depend on three parameters: beta, some real number, alpha, and some other parameter s. Alpha and s are positive. And this procedure that was initially proposed by Bayer, Macri, and Toda was shown to work for various examples, like funnel threefolds with the rank 1, the quintic threefold, abelian threefold. So there are a bunch of threefolds for which this procedure works, and there are a bunch of threefolds for which this procedure does not work. Right? So there are counterexamples. But these, this family of Bridgeland stability conditions here, depending on these three parameters, are called the geometric stability conditions. In the literature, they are called the geometric stability conditions. These things. So the important thing is now that this thing depends on three parameters. And one novelty is that the derived category itself is changing with the parameters. Right? So before we had perhaps the category of coherent sheaves of some other fixed abelian category and a family of stability conditions on a fixed abelian category depending on parameters. Now the category itself, the abelian category itself is changing. That's a challenge. So let's make an example. Let's do some case study. My personal favorite, P3. So here it's, and you always have to pick some churn classes. Right? So everything starts fixing some churn classes. So I'm going to fix those churn classes. So R is supposed to be the rank, and D is supposed to be a degree, right? Well, not a degree, like a second churn class. And I'm going to explain why this has a minus sign. So why this is something with a negative rank. Both R and D are supposed to be positive integers. And this is one very particular slice of that of those families of stability conditions. I'm picking beta to be 0, the parameter beta to be 0, and this bit of the plane here, this quadrant here, is just the alpha and s parameters, which are positive. And in this particular piece of those geometric stability conditions, there is a version of what is called the nested walls, right? So walls are sets for these parameters where the set of stable objects change. Right? So this means that over here, the set of stable objects is 1. When you cross this this blue line, the sum of the stable objects become unstable. Right? So the set of stable objects changes as you cross this these lines that I marked here. So a wall is a subset of those parameters alpha, beta, and s, for which the set of stable objects changes. Something related, in physics, I'm told this has something to do with phase transitions. Good. So what do I mean by nested walls is that in principle the walls can intersect one another. Nested walls means a situation in which the walls do not intersect one another. So in this alpha S plane, we have these walls. The walls are arcs of hyperbole. And the red wall, which is this wall here, I call it the vanishing wall because there are no stable objects below it, right? So in this region here, between the vertical axis and the red line, so this region here, there are no stable objects. The moduli space of a Bridgeland stable object is empty. So that's what I call this red, the vanishing wall. Maybe I'll talk about the blue line. The blue line, I call it the Instanton wall. Because every object that is not an instanton, in some sense, every object that is not perpendicular to O2 gets destabilized. The idea here is that you may have some stable objects on this infinity region. So you may have some stable objects above the blue line, but what the blue line does is kill everybody that is not an instanton, and only the instanton survive between the red and the blue walls. In this region that I'm calling the quiver region, is a region where this crazy category that you obtain by doing this trick twice is actually a category of representations of quivers. The Bridgeland stability condition is a key stability condition, a very well-known type of stability condition on the category of representation of quivers. So in the end, in this space between the red and the blue lines, what you get is stuff that looks like the perverse instanton that I mentioned before. I can go there.
The maybe abelian category that you get is
a category of representation of quivers.
I mean, in this region in between.
Yeah.
You're saying that the abelian category, the heart of the T structure, is instanton.
Yeah. They are instanton things.
Which form an abelian category?
Which form an abelian category? Well, the stable objects in this abelian category are instantons. That's what I'm trying to guess. Right? So the category will have other stuff, but the stable objects will be the instantons. So and they look like that, right? So in this the information behind these monads, well, this alpha, both alpha and beta are matrices whose entries are linear polynomials, right? So polynomials, homogeneous polynomials of degree 1. So alpha and beta are matrices whose entries are homogeneous polynomials of degree 1. And you can repackage this information, all the information contained in this complex, as a representation of a quiver that looks like this. In the case of P3, you're going to have 4 arrows. This is not surprising. So this is exactly it comes from the basis of spectral theorem. And the basis of spectral theorem is something that I guess, right, probably inspired the team, the ADHM team back in the day. So it's the same thing from the 70s, but now repackaged and rebranded with all sort of fancy and complicated words. Or re-understood in different ways.
But this is different from the quiver that describes the drives category of coherent sheaves on the P3.
Yes,
It's not the same.
it's not the same. On P3, you would have one more vertex. On P3, you have one more vertex and 4 arrows here. Right? So this vertex corresponds to O2. And the being perpendicular to O2 means nothing is going on here. Only going on in this bit of the, essentially that's what it is.
But also you have relations, so what happened with the relations?
Yes, there are relations. Okay, so it's part of the data. Right? So the relations is precisely the beta equals alpha. Right? So what's going on in that yellow region is that the stable objects can be understood as stable objects in the derived in the category of representations of a quiver like that, subject to some particular choice of stability condition. Okay. This is one slide with a lot of information just for shock value, which means that it's just to tell you that one can describe what happens at infinity in that alpha S parameter. Right? That alpha S plane, I showed you 2 walls, but there might be many more walls, right? Because there are finitely many walls. And after you cross all the walls at infinity, that's what a Bridgeland stable object looks like. Right? Satisfying 5 conditions. Complicated thing, never mind too much. What is important is that the perverse instantons are there. Perverse instantons are stable at infinity. They survive every wall, and they and they satisfy all these conditions. Right? So they are Bridgeland semi-stable for some particular set of values of the parameters. They are perpendicular to O2. That's the second condition there is equivalent to cumulative conventions. Stability condition, cumulative conventions, and fixing of the Chern pair. So this is the definition of what I'm calling now instanton objects. Right? So in particular, the shifted perverse instantons, or the perverse instantons that shifted one, they are instanton objects. So they will be stable objects in this yellow region. And I like this. This is the motto that the instantons are the last ones to die because they are stable at infinity. They cross a bunch of walls. They survive, right, up to when everybody dies. So they are the last ones to die. They are the last ones to be destabilized in this sense. But there are, but there is more stuff in some sense, right? So, so one specific case that we can, do all the calculations is this: when you take rank 0, so rank 0 instantons of multiplicity or 3. So these are objects in the derived category with that Hilbert polynomial, 3 times t plus 2. So here there are only 2 walls. So the picture is precisely this picture here. There's only the blue wall and the red wall. So there are only 2 walls, the instanton wall and the vanishing wall. Above the instanton walls, the stable objects are precisely the Gieseker semi-stable sheaves with that Hilbert polynomial. Right, so at infinity, what you get is the Gieseker moduli space. This Gieseker moduli space has 4 components. One component consisting of planar sheaves. So this is elliptic plane cubics, right? So this is not the Hilbert scheme, right? So the objects here are sheaves supported on curves. So P3 means sheaves of degree 0 on an elliptic cubic. R3 are the sheaves on a rational cubic, on a twisted cubic. Then this T21 is the disjoint union of a conic and a line. And then the other T111 is 3 disjoint lines, but with sheaves on it. It's not just a line, but a particular sheaf. So that you have that term character. So it has 4 components. In all of these 4 components, there is only one class of sheaves that are non-Instanton sheaves, which is this is the structure sheaf of a plane cubic twisted by 2. And these are the only non-Instanton sheaves. And they get this, so this is the only sheaf that gets destabilized at the Instanton wall, and they get destabilized in this other object over there. And this object is not is not in any previous list of instantons. So it's really a new class of instantons. So what I mean to say with this example, right? So these non-instanton sheaves that get destabilized at the Instanton wall and replaced by objects of that. And these objects of this form here, the O1 minus 1 shifted, so this is not a sheaf, right? It's a complex. And it's not a perverse instanton. It's not some kind of instanton that appeared before, right? So they are still quasi-isomorphic to the monad side complexes. So I mentioned this example to try to convince you that there are really more stuff, more instantons in this derived category than what we have seen before. So I studied in detail this case of P3, but it's possible to adapt much of what I said to the funnel threefolds with the Picard rank 1. There is some particular subset of the set of all stability, geometric stability conditions on X. So this set calligraphic U is some particular conditions on those parameters alpha, beta, and 0 and S. Then the Chern character would have to be that. So never mind too much what is the exponent beta on the Chern character. Just to fix one way to fix the Chern character. Except that as opposed to P3, in which between the blue and the red wall, there's no subdivisions, right? So there are no chambers in this region between the blue and the red wall for P3. For other funnel threefolds, there might be some further chambers. There might be some subdivisions in this region. This region U, which in the case of P3 is that region between the blue and the red lines, can be further subdivided in several chambers, and then we have a concept of an instanton object for one particular chamber. Instanton objects belong to the perpendicular of OQX. So they are some sort of generalization of the instanton sheaves on these funnel threefolds with Picard rank 1. But then we don't know them all, right? So we're still starting to explore other funnel threefolds to see what these instanton objects are in other funnel threefolds. So that's it. Thank you very much for your attention.